Have you ever heard that entropy is just disorder? Like when your room gets messier over time, people might say, that's entropy. Or maybe you've heard it in science class. Entropy always increases. The universe tends toward disorder. Chaos always wins in the end. Well, here's the thing. That's not really what entropy means. In fact, that whole idea of entropy being disorder is one of the most widespread misconceptions in science. It's not completely wrong, but it's misleading enough that it hides the actual beautiful truth. So, what is entropy? Why does everyone keep talking about disorder? And what does entropy really tell us about the universe? Let's start with where the confusion began. Back in the 19th century, when scientists like Rudolf Clausius and later Ludwig Boltzmann were developing thermodynamics, they were trying to explain why certain processes happen and others don't. Like, why does heat flow from hot to cold? Why do gases fill containers instead of staying in one corner? Why can you mix cream into coffee but never unmix it? To make sense of this, they needed a new quantity, something that could capture what changed in these processes. Clausius gave it a name, entropy. He defined it mathematically in terms of heat and temperature, and noticed that for isolated systems, entropy always increases. That became one of the pillars of thermodynamics, the second law. But what is entropy physically? That's where Boltzmann came in. He connected entropy with probability. Instead of thinking only about macroscopic things like pressure and temperature, Boltzmann asked, what are the microscopic particles doing? And how many different ways could they be doing it, while still producing the same macroscopic outcome? This was the revolutionary idea. Entropy is a measure of the number of possible microstates corresponding to a given macrostate. Let's unpack that with a simple example. Imagine a box of gas. All the particles could be bunched up in one corner. That's one very specific arrangement, a low entropy state, because there are very few microstates where that happens. But if the particles are spread out evenly across the whole box, there are huge numbers of possible arrangements that look like that. That's a high entropy state. And here's the kicker. Both of those macrostates might look similar to our eyes, but one is vastly more probable than the other, simply because there are many more ways to be that way. That's the heart of entropy. It's not about chaos or messiness. It's about probability. The universe doesn't prefer disorder. It just tends towards states that are overwhelmingly more likely. By the way, if you like this content, remember to subscribe and like. Now, to make this concept easier to explain, people started saying things like entropy is disorder or the universe tends toward chaos. And sure, sometimes a high entropy state looks more jumbled than a low entropy one, like a shuffled deck of cards versus a neatly ordered one. But that's just a visual metaphor. It can be useful when you're just starting out, but it's not the real definition. Let's go back to that deck of cards for a second. When you buy a new deck, it usually comes perfectly ordered. All the spades, hearts, diamonds, and clubs in sequence. That's one very specific arrangement. But once you shuffle it, the number of possible arrangements explodes. There are about 10 to the power of 68 different ways to arrange a 52 card deck. That's a number bigger than the number of atoms in the Earth. Almost every shuffled deck you've ever held is a completely unique microstate. So when we say the entropy of a shuffled deck is higher, it's not because it's messier or uglier. It's because there are more microstates that correspond to that kind of shuffled appearance. It's a matter of combinatorics, not chaos. Here's another way to think about it. Imagine flipping a coin 10 times. There's only one way to get all heads, but there are dozens of ways to get 5 heads and 5 tails in random order. That outcome isn't more disordered. It's just way more likely. Entropy is a way of measuring that likelihood. This is why the second law of thermodynamics works the way it does. If a system can move from a low probability state to a high probability one, it almost certainly will, because there are more ways to be in a high entropy state. It's not that the system is being lazy or falling apart. It's just that chance overwhelmingly favors the high entropy configuration. So when cream mixes into coffee, or perfume diffuses across a room, or your hot coffee cools down. It's not that nature prefers disorder. It's just that there are far more microscopic ways for those outcomes to occur than for their reverses. Now, let's touch on the mathematical definition, because it's elegant and powerful. Boltzmann gave us a formula, S equals K log W. Here, S is entropy, K is Boltzmann's constant, and W is the number of microstates. The more microstates available, the more ways the particles in your system can be arranged, while still producing the same overall outcome, the higher the entropy. That equation is actually engraved on Boltzmann's tombstone. That's how central it is to physics. And here's the really fascinating part. This statistical view of entropy doesn't just apply to gases and boxes. It applies to everything, from the formation of stars to the melting of ice, from the mixing of chemicals to the arrow of time itself. Entropy is deeply tied to why time seems to flow in one direction, why you remember the past but not the future, why the universe began in a low entropy state and has been increasing in entropy ever since. It's not about disorder, it's about the relentless march toward more probable configurations. So, next time someone tells you entropy is just disorder, tell them this. Entropy is really about information. It's about how many hidden details, how many invisible arrangements lie behind what we can see. Disorder is a metaphor. Entropy is math. And in that math lies one of the most profound truths of our universe.